On number 20, we are to find the vertical and horizontal asymptotes of the function and use limits to describe the corresponding behavior. Well, if we look at our horizontal asymptotes first, which I recommend you always do, we're looking at top-heavy, bottom-heavy, or matching. You remember from, I believe that was chapter 1 when we first discussed that. This one is matching degree, so that means that our horizontal asymptote will be y equals 3 over 1, or y equals 3. And remember, a horizontal asymptote occurs when the limit as x approaches either plus in positive infinity or negative infinity, and sometimes both. Is 3. So if analytically we've determined it's 3, it has to happen in at least one spot. Well, since this is a calculator problem, you can go ahead and graph it and see, or you can trust my picture here that this in fact is the picture, and it is, and we have a horizontal asymptote at 3. Now you also notice in our graph that we have no vertical asymptotes, but if you come back and look at your denominator, we knew that there would be no vertical asymptotes here because this is never 0. And the only way you get a vertical asymptote is if the denominator can be 0, but since we've verified with our graph what we presume to be true to start with, we know that we have limits, and the limit at infinity in both directions is 3. Alright, 24. Find the asymptotes and intercepts and graph the function. So again, let's do as much as we can without the calculator, even though we can use it. And since we noticed that this has a factorable denominator, let's take care of that first. And we're going to have x plus 2 over x plus 3 times x minus 1. And we get a 0 in the top of negative 2. And remember, your 0 from the top is your actual 0 for the function. That is, that gives you your x-intercept for the graph. So we'll go ahead and plot that value on our graph. And then we get vertical asymptotes anywhere a factor in the denominator equals 0, which means that we're going to have vertical asymptotes at x equals negative 3 and x equals 1. These will be our vertical asymptotes. Let's go ahead and put those on the graph. I do like to add these to the graph as I go. And so we have a vertical asymptote here. We have a vertical asymptote here. We have a horizontal asymptote at the x-axis because our function is bottom heavy, because the bottom is quadratic and the top is linear. So we had a 0 here, and that's all we had so far. Our y-intercept is going to be wherever, when you plug x in. So let's do f of 0 to get our y-intercept right quick, and we get from the top 2, and on the bottom 3 times negative 1, so that's going to be negative 2/3, which is going to be right here in this ballpark. So pause the video, grab your calculator, and graph this function, and then come back and see if what you get on your picture matches what I have on mine. And here is roughly where that section will come out. This one is going to come out right through here. Let me undo that, try to hit both those points better. And when you draw these graphs on your paper, you want to make sure that you hug the asymptote as closely as you can without actually touching it. And then we have one more section of this graph to include, which is right in here. We don't have to do any descriptions with limits on this one, so our work is done. On to number 42. Here we're to find the intercepts, asymptotes, use limits to describe the behavior at the vertical asymptotes, and analyze and draw the graph of the function. Alright, so let's start by factoring the top and the bottom. But let me move that down. We'll have a little more room to write. So the top is going to factor to x minus 2, x plus 1. The bottom is going to factor to x minus 4, x plus 2. Again, nothing cancels. Matching degree means that we're going to have a horizontal asymptote at y equals 1, the ratio of leading coefficients. And then we're going to have vertical asymptotes at x equals 4 and negative 2. So let's go ahead and put those on our graph. Vertical asymptotes at 4 would be there, negative 2 would be there, horizontal at 1. And you notice when we have two vertical asymptotes, we're going to end up having a 3-section graph, which means our domain would also be in 3 sections as well. So let's get our intercepts now. Excuse me. And the x-intercepts happen when the top is 0, so that's going to happen at positive 2 and at negative 1. Our y-intercept happens when x is 0, so we would do f of 0 equals negative 2, plugging into the factored form here, times 1 over negative 4 times 2. Well, that would give us negative 2 on the top, negative 8 on the bottom, so that's going to be positive 1/4. So we'll put a little dot at what appears to be positive 1/4. And see, I'm already thinking we're going to have something like this, because if it has those two zeros, it can't turn around and come back, because that would give us more zeros. And then if we go to the right, 1, 2, 3, 4, 5, that would give me 3 times, again plugging into that top, 6 over 1 times 7. So that's 2 and change, which puts me up in here somewhere. So it's going to go up and then come out and hug that asymptote as well. If I go to negative 3, that would be negative 5 times negative 2 over negative 7 times negative 1. So that's 7 on the bottom, 10 on the top. So that would be 1 and change. So I know my other section is going to be, ooh, that's ugly, up in here, like that. Alright, now let's look at our details here. Our domain is from negative infinity to negative 2, and I'm going to leave out my u's since I'm squeezed for space, but you can put u's between these sections to be correct. And then it would go from negative 2 to 4, and then from 4 to infinity. Our range is from negative infinity, remember you start at the bottom and come up, and the first time we run out of space there is somewhere under 1, so I'm okay if we call that 1. And then it jumps to the other side, which both of the top pieces are covered by this 1 to infinity above. Continuity on domain. That's an O, a terrible one. Alright, and then the increasing, decreasing. We have increasing on this interval, and in fact increasing on this interval till somewhere along in here, and then decreasing, and then decreasing again. So that would be from negative infinity to negative 2, and then from negative 2 to somewhere around, hard to tell on my picture, the way I've sketched it, I would say around 0, and then from 0 to 4, and then from 4 to infinity on the increasing, decreasing intervals. The symmetry is an NA because it's not even or odd, and it is not bounded, so we can say NA. You can do better analysis in more detail if you graph this on your calculator and trace to look for things like the maximum in this area, where you could talk about your local maximum and what specifically it is. But mostly I want you to make the connections between the equations and the graphs at this point. So how detailed you get on that is up to you. If you see the details in the answer in the back of the book, that's what they're doing. All right, let's go to 52. This will be our last example. And on this one, again, we're going to start by trying to factor it. And the top nicely has a little 2x that comes out there, and that gives us not an x there, but a 2x here plus 1 over, well, when we go to try to factor this trinomial, we got to remember we're looking for a pair that multiplies to positive 8 with a difference of 4, and that doesn't happen. So the denominator of this one is not factorable. So that tells you that in essence you're going to have to trust your graph on your calculator. But before we go there, let's see what we do know. We do know that because we have matching degree that we're going to have a horizontal asymptote at y equals 4. We do know that we're going to have zeros at x equals 0 from the 2x and at x equals negative 1/2 because of the 2x plus 1. And beyond that, there's not a whole lot you would be expected to know from this, so grab your calculator and take a look, and I'll sketch it here. You can pause the video or let it play while you graph up. That's up to you. But roughly, here's what your graph's going to look like. And I'll switch colors so that the graph stands out a little bit. And it's going to come in. Let's plot our intercepts. What did I say? 0 and a negative 1/2, so like right in here. And let's zoom in on that and see what happens there. Specifically, if you want to get a good sketch on your paper, and on all of these where you use your calculator, there should be a nice sketch on your homework to show what we are finding here. And I'm still zooming in on mine, and it's really, really close there. But it looks like we have a very slight little dip here where we've got those two intercepts. And I'm going to zoom standard and get this sketch. In fact, I think you have to zoom out a little bit to be able to see. And if you haven't done it on your calculator, zoom out a bit so you can see what I'm about to show you on this graph. And that is that we get this strange little wiggle going on in the middle where this dips down, comes up, peaks out, and that's a little too dramatic. Let me try to do a better job with that. And then on the left side, it just sort of scoops up and heads out in the same direction on this side, kind of flat lines, to where you would have that horizontal asymptote right there. That would be your horizontal asymptote at 4. The analysis they're looking for is the same things that were listed on the last problem. So you would look at boundedness, and this one would be bounded. This is a bounded function because we have a minimum and a maximum. So you should trace on your calculator to find those and record them. We do not have symmetry. Our domain is all real numbers. Our range would be the y-coordinate of your minimum to the y-coordinate of your maximum here. Continuity, it's continuous for all real numbers. And it is decreasing on this interval here, which looks to be from negative infinity to negative 1/2, and then increasing on negative 1/2 to, you'd have to see what the x-coordinate is right there, and then, so fill that blank in with your analysis, and then decreasing thereafter. So from whatever that value is out to infinity. And that's the analysis of that graph.